Hello, today I wanted to go over just a few practice problems over simple harmonic motion. In this first problem, let's say we have a spring system oscillating back and forth on a frictionless table. We know the mass of the block is 0.33 kilograms. We know the period of oscillation is 0.17 seconds, and we're trying to find the k value. A useful equation to know is that the time in seconds of a period is equal to 2 pi square root m over k. So if we have 2 pi square root the mass of the block over the k value is equal to our period, 0.17. All we have to do is have 0.17 over 2 pi squared to take care of that square root at this point is equal to 0.33 over k. So multiply k on each side, that'll take care of that, and divide by this guy gives us 0.33 over 0.17 over 2 pi squared. We'll give you the k value given the mass and the period of a spring mass system oscillating horizontally on a frictionless table. Here's another scenario. Let's say we have a block of mass 176 grams, pulled back 6 centimeters, and then set to freely oscillate back and forth. And we are trying to find the acceleration maximum. Well, we know that as it passes through its equilibrium point, right here, if it's oscillating back and forth, through its equilibrium point, we know we'll have zero acceleration, maximum kinetic energy. Maximum acceleration happens at the farthest pulled back or farthest extended positions. If it's 6 centimeters, we have two useful equations. We know the force of the spring is equal to the k value of the spring times delta x in meters, and we know force equals ma. So what we can do, since these are both forces, is we can set them equal to each other. So k delta x is equal to mass acceleration. Our delta x is from the equivalence point, so we have 0.06 meters, 6 centimeters. Our k value is given to us. It is 8 Newton meters. Our mass is given to us. We want to put that in kilograms, so it's 0.176 kilograms times our acceleration. So to solve for acceleration, we have 8 Newton meters times 0.06 centimeters over 0.176 kilograms will give us our acceleration in meters per second squared. Here's another scenario. Let's say we were to have 3 weights. We have three situations with a spring, 2 with weights. With no mass added, we can set this as our zero height. This is h equals 0. Okay, we know that adding a 7 kilogram weight puts the spring at 5 centimeters. And we know putting it at an unknown distance, or a known distance, adding an unknown weight drops us 5 plus 10 centimeters. So this is h equals 15 centimeters. So we're trying to find the mass. 2 ways to do this. We can calculate the k value knowing this force. So if we have our force is simply our force of gravity. So if we're solving for the 7 kilogram, since it's the same spring, it's 7 times the gravitational acceleration is equal to our k value times our delta x, which is 0.05 meters, because it's 5 centimeters. So our k value is equal to 9.81 over 0.05 meters. And we can use this k value with this new height of 15 centimeters to solve for the mass. Another way of thinking about this is the spring is the same, so the K constant is constant. Gravity isn't going to change. So we know if we're trying to find the mass, we have some sort of mass pulling it down 5 centimeters, and then a second mass pulling it down 3 times as far, 15 centimeters. 5 is 3 times smaller than 15. Therefore, we know that this unknown mass must be 3 times this 7 kilogram mass, giving us a mass of 21 kilograms. Just a couple different ways of solving for that one. Let's say we had another situation. If we had a child on a swing oscillating back and forth in simple harmonic motion, if we were to add a second child, how would that affect the period of oscillation? So all things else had constant. So if period 1 equaled T1, period 2 with that second child on it, what might that equal? Well, let's look at oscillation. The period of oscillation is equal to 2 pi times the square root L over G. Mass is not a variable in this equation. So we know adding that second situation, adding that second child, P2 is still going to equal T1. The two periods will be equal to each other because mass is not a variable we need to account for. So here's another situation. If period 1 in this situation went in a simple oscillating motion back and forth, and it took 2 seconds to do that. Well, what variables, length, mass, or amplitude, would we have to change if period 2 was 1 second? Well, let's look at the variables we can change. The period of oscillation is equal to 2 pi L over G. Well, we can't change pi, we can't change G, so we can change length. So if period is just equivalent to the square root of length, what do we have to change length to for the period to be half? Because 2 seconds, 1 second relative to 2 seconds is half. So half is equal to the square root of L, if we're simplifying, everything else held constant. So the square root of something is 1/2. We know that we would just do 0.5 squared is equal to L. So if L is equal to 1/4 the length, it should half the time. This is with small angle approximation, which I covered in my lecture video. A last problem, just something to think about. If we have potential energy versus time in here, if the potential energy is decreasing and increasing as this pendulum goes down and back up, what does the kinetic energy look like? Well, and the same could be said in a spring. The potential energy is its maximum here, its minimum here, and its maximum again here, back and forth. Well, the energy in a frictionless environment doesn't have anywhere else to go. So whatever energy, the potential, this is its max energy it can have. So I'll put that max energy it can have. And if that max energy is being made up by all potential, we know the kinetic energy will be equal to 0 at this point. Here the potential energy is 0, so we know it has to all be kinetic energy. And again, the potential energy is its maximum, so the kinetic energy must be at a minimum. And here we have a U shape, so in the kinetic energy we must have a U shape. All these two graphs are saying is that potential energy becomes kinetic energy, and then back to potential energy in a nonlinear way. I hope this was helpful. If you have any other questions, feel free to drop them in the comments. I'm Mr. West Science, and I'll see you next time.